So in the last lecture, we introduced the idea that F equals ma. So now we want to talk about units of force. So F equals ma. So in SI units, this is kilogram, and that is meter per second squared. So a unit of force would be a kilogram meter per second squared. And we call that a Newton. The symbol for Newton that's universally recognized is N. So we would say that N equals kilogram meter per second squared. So that is a unit of force. Now, often you have small things that don't accelerate very much. So if we were in class, we would have small objects that weigh a few grams, and they're accelerating a centimeter per second squared, so that we can actually measure the acceleration pretty easily, and it doesn't go shooting across the lab room and hurt somebody. Well, that's also mass, that's also acceleration. So we could define a unit of force that's a gram centimeter per second squared, and that is called a dyne. Now, the official abbreviation for dyne is DYN, which is why you never really see dyne as an abbreviation, because that's silly. You just take one letter off. That's not much of an abbreviation. Well, we have a gram centimeter per second squared as a dyne, and then we have a kilogram meter per second squared is a Newton. Well, are 1,000 grams in a kilogram. There's 100 centimeters in a meter. So that means there's 100,000 dynes in 1 Newton. So this is your conversion factor right there. Well, we also know that in British units, British imperial units, you have foot per second squared would be an acceleration. This is a slug, so there is a unit of force that is a slug foot per second squared, and we call that a pound. Okay. Okay. LB being the normal abbreviation for pound. Okay. Well, so we have a slug foot per second squared, and so that gives us the idea of a pound. Now this is a really interesting thing. A pound is a unit of force, and a kilogram is a unit of mass. So what's going on here? Well, we know we have an object right here. Gravity pulls down on it. And so gravity pulls down on it with a force. Well, if it has a mass m, you let go of it, accelerates g. Well, we know that the F equals ma, but g is the acceleration. So the force due to gravity is going to be mg. Okay, so what that means is that a pound is how hard gravity is pulling on something. A slug is the unit of mass. A Newton is how hard gravity pulls on something. And so this raises a really interesting sort of scenario. And that is, in some countries, you have somebody and they say, well, how much, what's this person? And what they do is they give the mass of the person, and the mass of the person is going to be in kilograms. In the United States, though, we don't give the mass of the person, we give the weight of the person, which is how hard gravity is pulling down on them. So we actually give the gravitational force, and in other countries they talk about the mass of something. And so that raises some like weirdness when it comes to units. It also means that frequently when engineers are using British units or using imperial unit or British imperial units, or they're using SI or what we often call metric units, that in one system of units you often talk about force, and the other system of units you talk about mass. They're not the same thing. And they're used in equations differently, and this is one of the issues that you run into. You have to be very careful at what you're doing so that you don't mess up. And that's, for example, how NASA lost the Mars Climate Observer spacecraft in the late 90s, is that the Lockheed engineers were giving numbers that corresponded to pounds of force, and NASA was using mass in terms of kilograms, and then they were talking about pounds of weight. Well, weight is not mass. Weight is a force, and so they weren't using units, and they didn't realize that the other group of engineers weren't using the same units. I mean, both units are okay. It's just you have to know what you're using, and so they ended up losing a spacecraft. So just kind of a little side note right there.